proceed on towards the analysis and stress recovery. So for the analysis, under the Analyze menu here, we would just select the global and local FEA. Now, basically, there are several options here for running, and essentially it changes these grayed out radio buttons down here. It'll bring up the same dialog here. So we said solve coarse mesh and all fine mesh is what's selected under that first option. If we said just the global FEA, you can see it's the same dialog, but this is pre-selected for solve the coarse mesh only. And I think it won't allow us to do the local FEA because we don't have any fine meshes defined in this model. So there are no fine meshes to run. But typically, you'll just select that top one for running the global and local FEA. These other options further down, limit state evaluation, this is a post-processing for the limit states to do failure analysis. And that's, I guess, in the next session. Individual panel evaluation is related to limit state evaluation. It just allows you to do a specific analysis on a either existing panel in the model or making up sort of a notional one just by the dimensions, thickness, whether what stiffeners it's got, what loads it's going to have. The hull girder collapse is, I think, the Alps stuff, and the legacy version of Maestro. Have actually never run the legacy version of Maestro, but it's still included in the software as an option for those who need it. So we'll just go into the current version for running the global and fine mesh FEA. And we've got multiple options in here. So at the top is how Maestro should handle the beams. And we have three options for eccentric beam, hybrid beam, and the modified eccentric beam. Typically for these standard level 2 models, I think we typically just run the eccentric beam formulation. If you go into the help, this can give you a better definition than I can. I believe it's under, there's a link to it under here. And this gives a description. So if you look under the, I guess it's under the C-bar beam, and it'll tell you about the hybrid beam and the eccentric beam types in here. I don't think it covers the modified eccentric beam that was listed, but this basically tells you the difference between the two formulations. And if you have any specific questions about, things like the formulations and things, that's an area where I would defer to Meg. So normally for, I think the hybrid beam is supposed to be from the help. It mentions that the hybrid beam, I think, is the better option for coarse modeling that's done. But as the model becomes more refined, the errors from the eccentric beam become less and less. And that's the one I think has normally been used for models of this type where we've got, say one element between stiffeners and 3 or 4 elements between frames. So that type of resolution. For stresses and reaction forces, these are pretty much usually just checked. For calculating stresses, you're most likely going to want to see all of the stresses throughout the model. You can restrict them to specific groups, but normally it's just left at all, and the box is checked to compute them. And calculate reaction forces will allow you to recover any of the reaction forces on constraints if they are defined. If you wind up using the inertia relief, it creates a virtual node at the CG, so it's sort of a virtual restraint, so it won't give you the actual reaction forces at the restraint if you're using just the inertia relief. It's sort of an auto restraint that's created when you don't have any defined in your model. For failure mode evaluation, for just doing running the model and reviewing stresses and deformations, we don't need to do any of the failure mode evaluations. This is the limit state stuff, so we'll go into that in the next session. Now, at this point, when you hit OK, it's going to start solving all defined load cases in there. Now, I don't want to do that quite yet because I have not gone through and done the hydrostatic balance and inertia relief on all the conditions in this model yet. So the first thing we want to do, because these are all hydrostatically balanced load cases, we want to go in here and do the hydrostatic balance, and we can say on all load cases. Come in here, you can see the details on how many cycles it took. But yeah, 2 cycles to achieve the right balance. And then we come back in, and now we do inertia relief on all load cases. And this will create that virtual point at the CG with a soft spring connection to the model and make up for any slight differences and account for any directions that aren't restrained or aren't opposed by restoring forces. This one takes a little bit longer. So, okay, so we did the hydrostatic balance and the inertia relief. So now we can come in and run the FEA analysis. So this will take a little bit. I forgot to try and correct. You may have seen that one message that went by on the screen. Now this is in the output tab. You can kind of view the progress. So this is where we started our run. And there are apparently 2 degenerate tries in the model. So they were collapsed to a line or perhaps a point. Most likely it's just a line in the model. But you can see Maestro just ignores it. When it's got 0 area, Maestro will just ignore that element. So it finished the first load case, and now it's got to get through the other 3. Now this will generate a separate file in the same folder that you're running your model. So you can see, we're running this model here, the half-hull model, and there is this new RLT file, the results file, that it created when this started, and it currently has nothing in it yet. On completion, it'll dump all the data into that file. And then if you were to close the model, when you open it back up, you can, as soon as you try and view results, it will automatically load the results file. It'll search for a results file using the same name as the model file. So if you change the model file name, you can change the results file name so it knows that's the associated file with it if you want it to load automatically. You can see it just finished the run, so our job's complete, and our results file is 13 megabytes, almost 14. Now it hasn't displayed any of the results yet, but we can just select this load condition and come into the results menu here. And we've got a number of options for what we want to see. The first option is whether or not we want to see the model in its original state or in a deformed state. So if we select deformed model, it can look a little crazy when you first turn that on. And this is because Maestro is going to select a scale factor to exaggerate all of the deformations in the hull, but it looks at the largest deformation in order to select what scale factor to use. Now, if we come back into the view options dialog, under deformation here, you can see we can control whether or not we display all of the deformations, X, Y, and Z, or we can restrict them to a certain direction. So we're only showing deformations in the X direction. So you can see some of these bulkheads have some significant pressure on them. We can change that from X to just Y and look at vertical displacements. All of our bulkheads are nice and straight, but our decks show quite a bit. And if we look at the magnitude of these, it's amplifying everything by almost 190. If we move that down to something a bit more reasonable, let's bring it down to 50 and see how it looks. Significantly exaggerated, but we still get a good feel for the original arrangement or the original geometry of the ship. And you get a good idea of relative displacements in terms of the sag in each deck, how much each one is deforming relative to the others. I'm going to turn that down a little more. We can break it down to, let's take it to 30. And you can see some of the dishing of the plate between stiffeners on the bottom. We can view we'll get into viewing the stresses later, but the dynamic query allows us to come in and view all the information about each one of these elements. So when we select the dynamic query, you have the option of what you want to display, and these are toggles if we want to see what pressure is applied. There's nothing up on the deck. Down low, there's nothing on that one. So we can see this is basically the hydrostatic pressure on each of these elements. Similarly, we can do stresses, but if we bring up the nodal dialog where we are querying nodes, this is just showing us the location in the vessel, but the nodal query allows us to bring up nodal force, deformation, and then the distance is a utility, so you can measure distances in the model. But basically, in terms of additional information, we can have nodal force and or deformation. These are toggles that will get added to what's displayed when we do the dynamic query of a node. So you can see at the top, it's all of the original information in there, but we turned on forces, so you can see the Fx, Fy, and Fz values as well, including the mass that's assigned to that node. Now that mass is not only the structural weight that's assigned to that node from all of the elements that are connected to it, it also includes masses assigned to it from the tank loads and the mass distribution. Actually, I take that back. It may not include the masses from the tank loads, but it does include the masses from the mass distribution that was assigned on there. And then you can see the dx, dy, dz, as well as the rotations about x, y, and z, which are shown in radians on here. Now, when you're doing a dynamic query, and this applies to whether you're doing a panel or a node, if you double click the values so that you don't have to keep hovering on a specific node and keep the dialog up, you can double click on it, and that all that information will get echoed into the output tab. And then you can cut and paste this into another area or into a spreadsheet or document if you want, or just continue viewing it here. And you can move around the model and click in different areas. If there's a specific set of nodes or plate areas that you're interested in, and we've done this in the past for, I think I had mentioned when we did that dry docking model, they had a set of optical sites along the wall of the floating dry dock, and there were like 6 sites down along the length that they would monitor each day to make sure that the dry dock was remaining flat. When we did our model, we created a nodal group and we recorded those specific locations along the hull and we made a nodal group. So if we come in here and let's say for whatever reason you have an interest in the displacements of this node, this node, this node, and this node, we can create that nodal group and we come in here and we view it. Well, it's just 4 nodes, doesn't mean much to us at this point. If we come in and do a dynamic query, well, because we're viewing a group, the nodal query isn't working. The straight query will just bring up the standard default information, X, Y, and Z values, and the FE tag. But since we're displaying this nodal group, another option we have here is to generate a list, and we can tell it to list the either elements, nodes, or reaction forces from the model. But if we tell it to list the node values, since we've already solved the model, it has the displacement and force information and everything. So those 4 nodes that we have in our group will get listed in the grid view. And we can see, the original XYZ locations for them. So that'll help identify which one's which. So if we sort by X, and we have 40, 60, 80, 100. So that's the first one, second one, third one, and fourth one here. They all have the same Z value. They're on center line, same height. First one is, there's a little bit of deck shear forward. So that one's a little bit higher than the others, but the others are all at the main deck. And we can see what the X, Y, and Z displacements are and the rotational displacements. There's the total displacement. And we can also see what forces were acting on those nodes in the X and Y directions here, and then the masses that were assigned to each one. And in this grid view, you can copy this information out, and if I hit Control A to select all, you can grab everything and then just right click and say copy. The other thing you can do, and I think we went over this once before, was in this particular view, if you wanted to cut and paste this into a spreadsheet, well, it would be nice to have those column headers in there. So what you can do is use the right click on one of the column headers and say change fixed rows and make the number of fixed rows 0. So you can see now it's displayed in white, and when you hit Control A, it grabs everything, including the titles, and you can copy those out, paste them into the spreadsheet, and then you'll have these available. The other nice thing is that now that you've defined the nodal group, you can view it regardless of which load case you're viewing. You can switch the load case to bring up the new data and relist the nodes, and you can see the updated values for the second load case. If we want to look at sagging, we can update them again. And the sagging deformation, if we come back and look at it in this view, it's not actually too bad compared to additional. So I guess it's the scale factor be lower by default on the sagging one. If we check the scale factor in here, and whenever you change views between loading conditions, it's going to auto scale the deformation value. You can change it manually, but it'll, like for sagging, it's auto scaling to 53.5. And with additional mass distribution in the still water condition, where there isn't, I guess, as much total deformation, it winds up using a higher scale factor because the plate hadn't deformed as much. So it's, almost 4 times higher, or about 4 times higher at 189. And the hogging condition, let's see what results we get there. Pretty good deck deformation in there. That's probably a higher scale factor. 88. So it's higher than the sagging was by default. But if it's just a quick query, you can just do nodes, and it'll remember from the last time you were querying nodes whether or not these were checked, and you can simply just hover and recover the information. Let's go back to the additional mass distribution, and we will reduce the scale factor again. We'll take it down to, say, 40. And we don't have to have the model deformed. Even if it's in its original geometry here, we can still query throughout the model and recover all of the result information, either from the nodes or if you turn on contours, that will color code the deformation. So we can turn off the deformed model. No, I guess it has to be deformed to show the contours. It's color coded by total displacement. And let's change the scale of the deformation. Now this won't change the scale of the coloring. So actually, if you wanted to see a color-coded, undeformed model, we could probably come in here and change the scale factor on the deformation to 0. So it's undeformed, but the colors indicate how much deformation there is in each area. Oh, I'm sorry, it won't allow 0. So scale factor of 1. Okay, so yeah. And if we bump this up to, say, 25, you can see sort of the deformed model with the color coding. I don't know that the inertia relief applied in here. I'll have to look into this. This might be because we're running the half model instead of the full model. You can see the deformation here. The total displacement is up at 0.32 meters at the aft end. You can see the color bars, where it runs from 0 to 3. It's similar along the length here. You have very little deformation at the bow and much higher deformation at the stern, and it's because it's sort of pitched. That doesn't seem quite right. Now that could be because of some of the issues with the half model that we were seeing earlier that it's being worked on now, or I thought I ran the inertia relief on here, which should put a soft constraint at the CG, and the model should sort of deform around the CG. The hogging isn't as bad, but the sagging does look odd. So that would be something that would want to review. It may not be an issue when we run the full model. Now, I did run inertia relief for each of these because you can see there's an additional acceleration shown. We didn't define that. That was defined by the inertia relief. And you can see in pitch, it's times 10 to the negative 5. Heave is times 10 to the negative 4, and surge is 0.04. Now, if we compare that to one of the other cases here, it's a little higher in surge than we got for the still water. If we compare it to hogging, well, it's actually about half of the x acceleration that we had from hogging. But you can see they're all fairly low accelerations. They're not in G's, they're meters per second. So pretty small values, which is what we would expect. But the inertia relief was run. So we'll have to try this with the full model and see if we get the same result with the sagging.